My name is Anastasia Sveshnikova and I represent Swiss Prod Group of Swiss Institute of Bioinformatics. Thank you for joining me today for this poster presentation on the project titled Advancing Rhea Database Annotation with EC Numbers using Reaction Fingerprints and Machine Learning. In this presentation, I will provide an overview of the project, the methods used, the results obtained, and the conclusions drawn. Let's dive in. The purpose of this project was to develop classification models based on reaction fingerprints for predicting EC and their commission classes for reactions in the Rhea database. The project aimed to achieve two main goals: partial EC prediction, which can be useful for identifying the enzymatic mechanism, and full EC prediction, which can be useful for annotating orphan reactions with proteins. In this poster, I will focus on predicting the reaction mechanisms that can be represented with a partial EC number, for example 111. Understanding the reaction mechanism can be useful for understanding the enzyme function, designing drugs and therapeutics, enzyme engineering and biotechnology, predicting enzyme behavior, for example kinetics, and evolutionary studies. To accomplish this goal, two methods for reaction fingerprint generation were tested: DRFP, differential reaction fingerprint based on circular chemical substructure extraction and hashing, and RxNFP, obtained from a bird model. Previous research comparing DRFP and RxNFP showed that while DRFP only slightly improves on the classification and prediction accuracies of other methods, its value lies in its conceptual simplicity, low use of computational resources, and reproducibility. Two machine learning models were tested: MLP, multilayer perceptron, and KNN, K-nearest neighbor classifier. The number of input nodes for the MLP was equal to the input length of the fingerprint vectors, and the number of output nodes was equal to the number of classes at the defined EC level, EC1, EC12, and EC123. FAIS, Facebook AI Similarity Search KNN algorithm, was used due to its computational efficiency for the KNN classification task. Application of DRFP plus MLP method was previously described by Probst in 2023 for annotating biochemical reactions with EC in the method called TEA, while RxNFP plus FAIS were used by Schwaller et al. For other chemical classification tasks. The results of applying fingerprints and classifiers to Rhea reactions showed promising outcomes. The FAIS KNN classifier achieved high accuracies for predicting EC classes at different levels, with DRFP outperforming RxNFP. The MLP classifier trained with DRFP showed excellent accuracy in predicting EC1, EC12, and EC123 levels. Furthermore, the analysis showed that predicting only EC123 is sufficient in most cases, as the model's accuracy for all EC levels is generally consistent. Only a small percentage of reactions would benefit from predicting EC1 and EC12 levels as well. We selected DRFP plus MLP as a method of choice. Here you can see the results of training the MLP models for DRFP or RxNFP for different levels of EC. As you can see, the MLP was trained using less epochs with DRFP fingerprints and achieved lower loss. RxNFP remained at high loss after more than 2 times more epochs of training. Based on these results, EC numbers were predicting for 8,000 reactions without curated ECs using DRFP plus MLP model. The predicted EC numbers were compared with EC numbers based on the extrapolation from the manually curated Rhea reaction hierarchy, which was possible for 2,000 reactions. Comparing the predictions with curated ECs revealed a low false positive rate. Only 120 predictions did not match the inferred ECs, with an error rate of 5.8%. The error rate decreased to 1.3% for predictions with a probability above 0.9. A probability cutoff of 0.9 was suggested as a reliable threshold for the predictions. In conclusion, this project demonstrated the successful application of classification models and fingerprints for predicting EC classes for Rhea reactions. The DRFP plus MLP model achieved high accuracy, interestingly even when predicting EC1 to 3 level. The results suggest that the developed models can be valuable tools for external researchers using the Rhea database. For this reason, the presented research is available as Jupyter notebooks. The next steps of this project involve further manual evaluation of the results by experts, refining the prediction thresholds, and implementing the final version for annotating all Rhea reactions with EC1 to 3. Ongoing discussions with enzyme database curators are essential to determine how the predicted EC Rhea cross-references will be incorporated into the enzyme database in Rhea. We are also exploring potential application in reaction similarity computation. This computation could be useful for building a reaction hierarchy of all Rhea reactions and for proposing catalyzing proteins for orphan reactions. Rhea development and curation activities at ISMB are supported by the Swiss federal government through SERI. Rhea development was also supported in part by the Swiss Lipids project of the System X, the Swiss initiative in systems biology. It was also supported by the Office of the Director, National Institute of Health. Thank you for your attention. I'm happy to address any questions you may have during the poster session.